Okay, so today we're going to be talking about solving systems of linear equations, which is a review of something that you've learned earlier. So we're going to go through, I'm going to start with the example from the last video, which is when we left off with the cell phone companies. We had two equations, right? The cell phone plan that started at $100 and then 10 cents per text message, and then the other plan that was charging 25 cents per text message. Let's say we wanted to solve it. Well, there are three methods that we can use to solve a system of linear equations. We've talked about it in class a little bit: substitution, elimination, and graph. I'm going to go ahead and solve this using substitution. All right, so we know that 0.10x plus 100 is equal to y, and 0.25x is also equal to y. 0.25x. So if I consolidate the x's, I'm going to subtract 0.10x from each side, and I end up with 100, because these cancel out, is equal to 0.15x. So x will be approximately 667. So this gives me the x-coordinate of the point of intersection, and then when you plug this back into either one of these equations, I think you end up with a y-coordinate that's approximately 167. So the answer to this system, which is where the two lines intersect, is at 667, 167. Or in other words, if you think about the cell phone example, after your 667th text message, one phone is going to have a higher rate, or you're going to be paying more for one company than the other, okay? So this is a simple example from last time where we're talking about two variables in a system, and that represents the point in which those two lines intersect. Now, I'm going to throw out here another general example, and I'll call this example number 2. Okay, and in example number 2, we're going to have three variables, okay? And so the first equation is 3x plus 2y minus z is equal to 8. And then negative 3x plus 4y plus 5z is equal to negative 14. And then x minus 3y plus 4z is equal to negative 14. Okay. Now, because we're adding another variable, z, we're not graphing lines anymore. We're adding another dimension. So these represent, each of these equations represent a plane, like a sheet of paper. There's some good diagrams in your book that you can check out to visualize kind of what's happening. But still, the same three methods apply. You can still use substitution, elimination, or graph, although I'm not going to lie, it's hard to graph a plane, especially on a two-dimensional space, and try to get like a point of intersection. So in this case, this problem is calling out to me to use elimination because I have 3x and a negative 3x, and that's just tempting to want to eliminate that first because it almost seems like it's ready to go. So if I number these equations, let's call this equation number 1, 2, 3. I'm going to start off by taking equation 1 and adding it to equation number 2 so that I can eliminate these x's here. So I have 3x plus 2y minus z is equal to 8, and negative 3x plus 4y plus 5z is equal to negative 14. When I add these together, the intention of eliminating the x's happen, and you get 6y plus 4z is equal to 8 minus 14, which is negative 6. So I end up with this equation. It's not really my solution, but I'll call it equation number 4 because that will help me with trying to solve the problem later on. So I'm going to try to do a little bit more elimination because it would be great to have another equation that has only a y and z in it. I'm going to use equations 2 and 3, and because this is already negative, all I have to do is add it to 3 times this equation. So I'm going to take equation number 2 and I'm going to add it to 3 times equation 3. And so I have negative 3x plus 4y plus 5z is equal to negative 14. And I'm going to add it to 3 times equation 3. So that's going to give me 3x minus 9y plus 12z is equal to 3 times 14, which is 30 plus 12, negative 42. These cancel out, and I get 4 minus 9, which is negative 5y. 5 plus 12 is 17z, and negative 14 minus 40